So in this video, what I want to do is just do a few examples of calculating flux for a vector field. And we'll start with just some really simple examples. So let's start by first of all defining the vector field that we're calculating the flux of. So let's first start with a sort of simple velocity field. Right? So this is representing what the velocity of some particles are. And we'll say that's a function of the position that we're at. And so just for the sake of argument, let's start with a sort of simple velocity field of xi hat plus yj hat. So we're in R2 here, right? And we've got particles that are moving at a velocity that depends on where they're located. If I draw what that vector field looks like, right, the further away I get from the origin, the larger that velocity is. Notice that it's always radially directed. This is supposed to be radially directed. And in fact, I could rewrite this in cylindrical coordinates as simply r times r hat. Right? So that's what my velocity field is. It's a vector field. Notice it's a quantity that's a vector that's defined at each point in space. I'd like to calculate what the flux of, say, particles are that are moving at this velocity. And so I'm going to combine that velocity field with some scalar field, which is the density of particles. Right? So rho of r is my density of particles. And for the sake of argument, let's just say that the density of particles is constant. Right? And finally, I need to not only have what my sort of fields are that I'm dealing with, I also need to know what I'm calculating the flux through. So let's say that I've got a circle, and I'm interested in asking the question, how many particles are passing out of this circle per unit time, right? So what's the flux out of this closed contour per unit time? For number of particles per unit time, what's the flux that's coming out of that? So to do that, conceptually what I'm going to do is integrate around this closed curve, right? So I'm going to integrate around the closed curve, and I want to ask the question, how much stuff is passing through each little chunk here, right? So I'm going to have my density times my velocity, right? You'll notice that this density should be in number per meter squared, right? So this is going to have quantity of units of number per meter squared times velocity, which is going to have units of meters per second, right? So right now it's numbers per meter per second, right? Dot n hat times dl, right? So if I look at the units here, dl is going to have units of meters, meter squared, cancels with meter squared, number per second. It makes physical sense, right? So let's now go and actually do this a little bit more carefully in a coordinate system, right? This is my coordinate-free version of the integral. This pretty clearly is a case that calls for me to work in the polar coordinate system. So I'm going to integrate from theta equals 0 to theta equals 2 pi, right? So I'm going to go once around this circle. My dl is simply going to be whatever the radius of this circle is, so let's call that big R. So r d theta, that's the length of a little chunk here that has thickness where my differential angle is d theta, right? N hat, well, n hat for this case is going to be a normal vector to my little chunk of length, right? So at each point n hat is going to be in the r hat direction, right? So n hat here becomes r hat. My velocity is r in the r hat direction, and my density is some constant, right? So r hat dot r hat is 1, so I have the integral from 0 to 2 pi of rho times r, but r is simply equal to r since I'm integrating around this surface, little r is equal to big R times n hat is dot n hat is 1 times big R is r squared times d theta, right? In other words, I get 2 pi times rho times r squared. Now let's think about why that might or might not make sense. What's happening when I draw a bigger circle? Well, when that circle gets bigger, two things happen. One is that obviously the length of the contour gets larger, right? And that length of the contour increases as in a way that's proportional to what r is. But the other thing that happens is as I go further out from the origin, the length of the velocity vector is bigger. In other words, the particles are moving faster as I get further from the origin. So that also gives me additional flux, which is why it sort of makes sense that this is r squared. One of the r's is from the length increasing, and the other of the r's is from the fact that the velocity gets larger as I go further from the origin. Okay? So that's one example of calculating flux. This obviously is an example in a polar case. We'll also do a Cartesian case in the next video.